Hello everyone and welcome to the latest installment of the IGCSE 0606 Solution Guide series. In this video we will take a closer look at paper 2.1 from the May-June exam period of 2021. So let's get straight into it. In exercise 1a of this exam paper we are supposed to write the expression x squared minus 6x plus 1 in the form of x plus a squared plus b, where a and b are constants. This can be achieved by completing the square as follows, whereby we divide the coefficient of x by 2 and square its result. Subtracting the same number does not change the equation. Since negative 6 divided by 2 is negative 3, and by consolidating negative 9 and 1, we have achieved the task. In part B, we are supposed to write down the coordinates of the minimum point of the curve from above, and this form allows for us to easily read those coordinates, which are positive 3 and negative 8. Positive 3, not negative 3, since 3 minus 3 equal 0, providing us with the offset of the minimum point across the x-axis from the origin. Next on to exercise 2, where it's said that x and y are such that when the natural logarithm of y is plotted against the natural logarithm of x, a straight line graph passing through the points 6, 5 and 8, 9 is obtained. We are supposed to show that y equals e to the power of p multiplied x to the power of q, where p and q are integers. In the first step we will obtain the equation for the straight line passing those 2 points mentioned. In the first step we will determine its gradient using the formula provided. To obtain the y-intercept of that particular line, we will plug in the gradient and either pick the coordinates of point 6, 5 or 8, 9 to substitute those for x and y in the formula. In this case I've opted to choose the first point, the other one also providing a valid method for finding c. Rearranging this equation for c lets us conclude that the value of c is negative 7. Therefore, the line graph that we've been looking for can be expressed by the equation y equals 2x minus 7. In a second step we should show that y equals e to the power of p multiplied x to the power of q. Since ln y is plotted against ln x, we can transform the equation for the line graph as follows. From here we rearrange this equation for y, which is achieved by exploiting the fact that the e function is the inverse of the natural logarithm. Using the laws provided we can simplify this expression to e to the power of negative 7 multiplied x squared. Next on to exercise 3, where in part A we are supposed to solve the inequality of the absolute value of x minus 1 being larger than 9. To approach this inequality we will in the first step square both sides of it and rearrange it from 0. From there, employing the quadratic formula, we will find our solutions for x. Doing so with the help of our pocket calculators will deliver us the results of negative 2 and 5 over 2 respectively. For the left-hand side of the inequality being larger than 0, we need to make sure that the multiplication x plus 2 multiplied x minus 5 over 2 is larger than 0. To ensure this, we need to keep in mind that either multiplying two positive factors or two negative factors will provide us with a positive result. Therefore, in the first case, inspecting the number line, in order to ensure that this multiplication yield a positive result, we need to make sure that the values of x need to be larger than 5 over 2, and in the other instance for both factors to be surely negative, we need to guarantee that both x values are less than negative 2. In part B of the exercise we are supposed to solve the equation 2x minus 11 times the square root of x plus 12 equals 0, and looking at the variables we can determine that we are dealing with a biquadratic function, since the exponent of x to the power of 1 is twice as large of that of x to the power of 2, since this is a representation of the square root of x according to the laws of exponents. Using provided methods to facilitate factorization of this equation lets us rewrite it as follows. From there we can firstly factorize the square root of x, and for the latter to summons negative 4. In the following step we are able to factorize both brackets as they are the same, providing us with the following factor representation of this equation. Here we can exploit our knowledge that a product equals 0 if at least one of their factors equals 0, so we will inspect this for both cases, providing us with two solutions for x, namely 9/4 and 16. Moving on to exercise 4, where it's stated that the graph of y equals a plus 2 tangent bx, where a and b are constant, passes through the point 0, -4, and has the period of 480 degrees. Part A of the exercise demands from us to find the value of a and b. To determine the value of a, we can exploit the knowledge that the graph passes through 0, -4, whereby the value of a represents the shift of this trigonometric function along the y-axis. Therefore, a has the value of -4. To determine b, we will make use of the information that the period of this trigonometric function is 480 degrees. To do this, for the reasons provided, we will set up the equation of 480 equaling 180 over b, whereby rearranging this equation for b, we can conclude that its value is 3 over 8. In part b of this exercise, on the axis, we are supposed to sketch the graph of y for values of x between 0 and 480 degrees. Since we are working with a function in terms of tangent, the vertical asymptote of this function is located right at the middle of our period, crossing the x-axis at 240 degrees. Furthermore, since a is -4, this will represent our horizontal asymptote for this function. As the coefficient of tangent x is positive, this is the only way for the sketch to correctly represent a aforementioned trigonometric function. Otherwise, the graph would be mirrored to the line y equals -4. Next on to exercise 5, where we are provided with two curves which intersects in the origin and at the point A. We're supposed to find the equation of the perpendicular bisector of the line OA. In order to find where two curves intersect one another, we will have to equate both of them, already knowing that one of the points where they intersect one another is the origin, the other solution automatically providing us with the coordinates for A. To make this happen, we will substitute y for x squared, inserting x squared here, leading us to the following equation of x squared to the power of 2 equaling 27x. We will arrange this equation for 0, factorize x. Since our result is 0, either x or the expression x cubed minus 27 must equal 0. Since we already know that for x equals 0, the y value will be 0 as well, as it represents the origin. We just need to look closer into the second option, providing us with x equals 3, which is the x value for the point A. Substituting 3 for x, we can conclude that the y value of the point A is 9, leading us to the conclusion that point A has the coordinates 3, 9. To find the perpendicular bisector, we now need to find the midpoint of OA using the formula provided, delivering us the coordinates for the midpoint, which are 3 over 2 and 9 over 2. To determine the gradient of the bisector, we firstly need to find the gradient for OA, M being located halfway between O and A. And since the bisector crosses OA perpendicularly, using the formula provided, we can from there easily deduce that the gradient of the perpendicular is -1/3. To find the y-intercept of the perpendicular line, we simply plug in the gradient of the perpendicular as well as the coordinates of the midpoint of OA into our formula and rearrange it for C. Therefore, our perpendicular line is represented by the equation. Moving over to exercise 6 of this exam paper. Here it is stated that variables x and y are such that y equals e to the power of x over 2 plus x cosine 2x, where x is in radians. We should use differentiation to find the approximate change in y as x increases from 1 to 1 plus h, where h is small. To achieve that, we firstly differentiate the e function employing the chain rule, and for the latter part we will have to employ the product rule. Consolidating our result provides us with the following expression. To figure out the approximate change in y as x increases from 1 to 1 plus h, we multiply the derivative of our original function with h and substitute our variable x for 1, after which we obtain our solution, which approximates to -1.41h. Next on to exercise 7, where we are supposed to find the exact values of the constant k for which the line y equals 2x plus 1 is a tangent to the curve y equals 4x squared plus kx plus k minus 2. Tangent of the curve means that the tangent touches the curve in exactly one point, So to find that point, we equate the line of the tangent with that of the curve, rearrange the entire equation for 0, and factorize x here in order to achieve a quadratic equation of the form ax squared plus bx plus c, whereby a is represented by the coefficient of x squared, which is 4, b by the expression k minus 2, and c by the expression k minus 3. Using this knowledge, we can employ the quadratic formula to find our solution. Since there is only one solution, as a tangent touches a curve at a specific point, we need to ensure that the determinant is at least 0. Expanding the determinant provides us with the following inequality. Thereafter we expand the whole square, consolidate our results and keep it rearranged for 0. And in this instance here we can apply the reduced quadratic formula, since the coefficient of k squared is 1, providing us with two solutions, namely 10 plus or minus the square root of 48. Next on to exercise 8. Here it is stated that in this question a, b, c and d are positive constants. And in the first leg of exercise A, it is stated that is given that y equals the logarithm with base a of x plus 3 plus the logarithm with base a of 2x minus 1. You're supposed to explain why x must be greater than 1 over 2. And the reason for that is that logarithms of negative numbers are not defined. Therefore, this equation is defined for x larger than negative 0.5. The reason being 3 minus 0.5 is 2.5, and from there the x values are only getting larger, meaning the value for this expression is only getting larger as well. And in those brackets, if we were to substitute x for negative 0.5, the expression would be 0. Thus, every number larger than negative 0.5 provides us with a number that is larger than 0. That's why this equation is defined for x larger than negative 0.5. In the second leg of exercise A, we are supposed to find the exact solution of the following equation, where in step 1 we multiply both sides of it with the denominator of the expression to the left-hand side of the equation. Thereafter, using the property for logarithms, we rewrite the right-hand side as follows. And as now on both sides of the equation we are working with a simple logarithmic statement with the same base, in this case a, we can simply eliminate the logarithmic expression, apply the square root on both sides of the equation, and receive two solutions for y, namely negative 3 plus or minus the square root of 6. In part B of exercise 8, we are supposed to write this expression in the form c plus d multiplied the logarithm with base a of 9, where c and d are integers. In step 1 we will rearrange the base of this part of the expression using the method provided. From there we further apply properties for logarithms, which are provided as well. As per definition, the logarithm of a specific base value, that same base, equals 1. After which we can substitute this expression for the simplified 1 over here. At this stage we can now provide a solution as required, since all of the logarithmic expressions are those of base a. In this step we can simplify logarithm with base a of b, and the reciprocal of 1 over 2 equals 2. At this stage here we simply expand the brackets and consolidate our result by collecting like terms, providing us with a result that fulfills the requirements of the task, whereby c has the value of 2 and d the value of 3. Moving on to exercise 9. Here we are provided with a curve that is such that its second derivative equals to the expression of sine 6x minus pi over 2. It is given that the value of the first derivative is 1 over 2 at the point pi quarters and 13 pi over 12 on the curve, and we are supposed to find the equation of the curve. Provided with those two statements, we are aware of the two following facts. Firstly, that f of pi quarters equals 13 pi over 12, and secondly that at the coordinate pi quarters the first derivative is 1/2. To find the first derivative, we will have to integrate this expression. We will have to integrate sine and thereafter apply the chain rule. Integrating sine is negative cosine, and within the brackets we will have to apply the chain rule. As the derivative of 6x is 6, this needs to be counted by dividing this expression by 6 to receive 1. From there we can derive that this expression represents the first derivative. In order to find the value for c, we can now make use of the first equation up here. Substitute x for pi quarters and equate this expression with 1 over 2. Rearranging this equation for c will deliver its value. Therefore the first derivative can be written as negative cosine of 6x minus pi over 2 over 6 plus 1/3. From there we will apply the same method to find the equation of the curve f of x. Again, we will have to integrate the first derivative of that very function, which again is done through the employment of the chain rule, whereby the integration of negative cosine is negative sine. And again, since the derivative of 6x is 6, we will have to multiply this entire expression by 1 over x. The integration of a constant is the constant itself multiplied by the argument, which in this case is x, plus a constant which we will name d, since we have already used c. Since this expression represents f of x, we can now determine d using our knowledge that f of pi quarters equals 13 pi over 12. Rearranging this equation for d will provide us with its value, which is pi. Therefore, this expression represents the equation of the curve. Next, on to exercise 10 of this exam paper, where we are working with vectors. It is stated that relative to an origin O, the positive vectors of the points A, B, C, and D are as follows. In part A of this exercise, we are supposed to find the unit vector in the direction of AB. For that, we firstly determine the vector for AB by subtracting vector OA from vector OB. Since we are required to find the unit vector, in a second step we will have to find the magnitude of this very vector using the formula provided, which provides us with the answer that magnitude is the square root of 80. Unit vector means that we need to ensure that this vector is of length 1. Therefore, we have to divide the vector by the length of its magnitude. In exercise 10b, the point A is supposed to be the midpoint of BC, and we're supposed to find the value of x and y. For A to be the midpoint of BC, A needs to be the equivalent of 1 over 2 multiplied B plus C, which provides us with the following equations, enabling us to determine those values and rearrange the equation for the vector x, y. Dividing those vectors horizontally will provide us with the values of x and y respectively, namely x equaling 2 and y possessing the value negative 13. In the final part of exercise 10, it is stated that point E lies on OD, such as the relation of OE and OD is 1 to 1 plus lambda. You're supposed to find value lambda such that vector BE is parallel to the x-axis. So in step 1 we make use of what is stated in the exercise and we rearrange this equation for vector OE. Graphically, this fact can be represented as follows. For BE to be parallel to the x-axis, the y values of B and E need to be the same. The reason being that this can be graphically visualized as follows. Let's imagine we are provided with points B and E, and for OE being parallel to BE, both of those need to be located on the same line. And for this to be the case and at the same time being parallel to the x-axis, both of their y values must be identical. So we can now simply equate B for this equation here. And since we just need to ensure that the y values are equal, we will simply take a look at this equation entirely from the perspective of the y values of the vectors. X can be ignored. From there we are deriving this equation here, 3 equals 7 over 1 plus lambda, and rearranging this equation for that variable provides us with its value, namely 4 over 3. Moving on to the penultimate exercise of this exam paper, which deals with progressions. It is stated that the second, 8th and 44th terms of an arithmetic progression from the first 3 terms of a geometric progression. In the arithmetic progression, the first term is 1 and the common difference is positive. In part 1 of exercise A, we are supposed to show that the common difference of the arithmetic progression is 5. So in terms of the arithmetic progression, we know that the first term is 1, and to find our second term from there, we need to add the common difference d to the value of a1, which is 1. Again, employing the fact provided, the 8th term can be found by adding 7 times the common difference to the value of the first term, and the same accounts for the 44th term of the arithmetic progression. To progress from there, we can now use the information provided in terms of a geometric progression. It is named that the value of the second, 8th and 44th term of the arithmetic progression are equivalent to the first 3 of a geometric progression. To determine r, we would divide a term with its predecessor, Since we know the first three terms, this can be done by dividing the third and with the second term and the second term with the first term, each of which would provide us with the factor r. So from here we can set up an equation in terms of d, which is desired as we are looking to obtain the common difference of the arithmetic progression, and we need to prove that it is 5. So in step 1 we will cross multiply the entire equation and from there expand the brackets on both sides of the equation. From there the equation is arranged for 0. At this stage here we can factorize 6d, again exploiting our knowledge of the fact that for product to be 0, at least one of the factors needs to be 0. So either d is 0, which is not the result that we are looking for, or the expression d minus 5 equals 0, which rearranged for d equals 5, which was to be shown. In the second part of A, we are supposed to find the sum of the first 20 terms of the arithmetic progression, which can be done with the formula provided, and we simply need to plug in all of the values as required. So since we are looking at the first 20 terms, we need to plug in 20 and d is 5, delivering us the solution that the sum of the first 20 terms of the arithmetic progression is 970. In the first part of part B of exercise 11, we are required to find the fifth term of the geometric progression. From exercise A, we are aware of the relationship between the second and eighth term of the arithmetic progression and the first and second term of the geometric progression, and we will further make use of the fact that d equals 5. Using those pieces of information will help us in finding r, so we know that a term divided by its predecessor delivers us the exact same thing. And as previously mentioned, we will substitute d for 5 and obtain r, which is 6. From there we will exploit the formula provided to find the fifth term of the geometric progression and conclude that it is represented by the value of 7,776. The second part of B, we are supposed to explain whether or not the sum to infinity of this progression exists, and the answer for that is that it does not exist for this geometric progression, since the value of r is larger than 1, and the sum to infinity of a geometric progression can only exist for values of r less than 1. Having arrived at the final exercise of this exam paper, we are provided with a diagram that shows us part of the curve y equals 9 minus x multiplied x minus 3 and the line y equals k minus 3, where k is larger than 3. The line through the maximum of the point of the curve parallel to the y-axis meets the x-axis at A. The curve further meets the x-axis at B, and the line y equals k minus 3 meets the curve at point C, k minus 3. We are supposed to find the area of the shaded region. Firstly, we will use the equation of the line and determine the coordinates of A and B. In step 1, we will rewrite the equation of the curve by expanding both brackets, delivering us the following expression, negative x squared plus 12x minus 27. And we are receiving a hint here that our equation is probably right, since the coefficient of x squared is negative, indicating that the parabola is opened at its bottom. This step, though, will actually help us at a later stage in order to determine the variables for a and b. It is sufficient to look at each of the factors, providing us with information on where the parabola intersects the x-axis, which is at point 0,9, which is b, and at the first point represented by the coordinates 0,3. Since quadratic functions are symmetrical, and we know from the fact that the line through the maximum point of the curve that is parallel to the y-axis meets the x-axis at A, that A is the halfway point between the points 0,3 and B, and since 6 is halfway between 9 and 3, the coordinates of A must be 0,6. Next on, we will attempt to find k, which will be done by using the fact that the line y equals k minus 3 intersects our quadratic function in point C. Here we will now use, instead of this representation here, following representation that has been calculated previously, equating this with k minus 3, and we will range the entire equation for 0 and multiply both sides of it with negative 1, which enables us to use the reduced quadratic formula to determine the values of k, which in this case are 11/2 plus minus the square root of 25 quarters. From there we can now determine the area that is shaded in red, providing us with two solutions for k, namely either 6/2, which is 3, or 16/2, which is 8. Since according to the exercise k must be larger than 3, only one solution is valid, namely that k must be 8. Knowing that k is 8 means that the area that's shaded in red needs to be inspected within the interval of 8 and 9. The curve can be integrated using the method provided. After plugging in 9 and 8 for our argument x, we will be able to conclude that the area mentioned has the size of 2 2/3. To that we will have to add the area of this rectangle. And since we know that k is 8, we know that this line can be represented by y equals 8 minus 3, which is 5. So the height is 5 and the width is 2, since 8 minus 6, which we know from the y coordinate of our point A, 2 multiplied 5 equals 10. So adding 10 to the size of the previously calculated area provides us with the area that is shaded in gray, and we receive that this area has the size of 12 2/3. I've been your host Marco from PlanetMaths. Should you derive any value from my videos, please consider to leave a like, comment and subscribe. Thank you for watching. Cheers.